So today we're going to be talking about chapter 11. Now, if I go too fast, let me know. If I go too slow, let me know. We can finish 3 chapters in a session. Okay, so we're going to talk about electromagnetic radiation. So energy is in the form of electricity and magnetic waves. So this is going to include your gamma rays, your X-rays, UV light, infrared light, visible light, microwaves, radio waves. All of that is forms of energy, right? How many of you guys use your cell phone? So you know you're putting energy in your head, right? Quite a bit, okay? So now the thing is that all of this energy, all of these electromagnetic radiations, they basically are going to be transmitting at the speed of light. So they're going to be traveling at the speed of light, okay? Now, and that is going to be 3.00 times 10 to the 8 meters per second, okay? Now, speed of light is considered to be constant. So it's always going to be that value, okay? It's always going to be 3.00 times 10 to the 8 meters per second. Now there's an equation because of the properties of light. We're going to be using what we call the wavelength and frequency. Now, I'm going to introduce you guys to a couple of Greek letters. Okay, wavelength is signified by lambda. So let me answer this question. So Yolanda, the homework for chapter 11, which is this chapter, is not going to be due until next week. So I know it says that you guys had 6 hours. It should be changed. If you check on it, it should actually say that it's due next week. Lambda. Okay, you're making fun of my 3rd grade handwriting. No, I'm going to go home and cry. Okay. Oh, okay. It's L-A-B-D-A. Lambda. Okay, and then frequency. This is a Greek symbol, and it looks like a V, but it really is like this. This is what it looks like. That's the way it's supposed to, right? And it's called nu. Like I have a new pair of shoes, so it's spelled in you. Okay, lambda and nu. Now you guys know Greek alphabet. Okay, so the equation is C equals lambda nu, where C is the speed of light, and lambda is the wavelength, and nu is the frequency, right? And you guys already know because these guys are multiplied by each other on the same side, they're going to be inversely proportional to each other, meaning as one goes up, the other one has to go down. Always because C is held as constant, okay? So if I'm given the frequency, right? So let's say, for instance, you guys, if you guys go to, you have phones, right? Everybody has a phone. Go to Active Learning. Sorry, I couldn't remember what it's called. Itzy, are you there? What was the problem that we did earlier?
The ones that we did earlier?
Okay, it says the frequency of green light has a wavelength of 531 nanometers. Speed of light is equal to 3.00 times 10 to the 8th meters per second. So we know that the equation is going to be C equals lambda. Okay. So if we're going to solve for this, we know that, again, lambda is wavelength and the frequency. So we don't know the frequency, so we want to solve for the frequency. So we want this equation solved for nu. You don't see it? Question number 5. Okay, so in this case, we look at our units. We have nanometers, and this is meters per second. Do those units pair up? No. Okay, so nanometers. How many nanometers are in a meter? Or how many, 1 nanometer, how many meters is that? So 10 to the, that is correct. 10 to the 9 nanometers will equal 1 meter, or 10 to the minus 9 meters equal 1 nanometer. So that's going to be our conversion. So we need to convert so that our units are matching. Okay? So that's going to be our very first thing that we need to do. So if I have 531 nanometers, for every 1 nanometer, that's going to be 10 to the minus 9 meters. So my answer is going to be for, I should say, this part is going to be, sorry, 5.1 times 10 to the minus 7. So now that I have my units matching up, I can just plug it into the equation. Speed of light is 3.00 times 10 to the 8th meters per second. And then we divide by 5.31 times 10 to the minus 7 meters. Meters are going to cancel out. And then we're going to be left with whatever value that we have in 1/seconds. Now, 1/seconds is the same thing as saying it's equal to seconds to the minus 1 power. They're going to be equivalent to each other. So if you see something to the negative 1 power, that's always saying 1 over this, whatever that value is. Okay. So, and this is also equal to a hertz. Okay. So who's going to do the heavy lifting?
Dr. Henry, isn't it 10 to the negative 9? It's 5.31 times 10 to the negative 9 meters.
No, it's since this is 531, right? So then that's the same thing as saying 5.31 times 10 to the second power, right? So this is to the second power, this is to the minus 9. So altogether that should be to the minus. Okay. So that is correct. So we have 3 significant figures. So my answer should be 5.65 times 10 to the 14. Okay. So we have a very small value for wavelength. We have a very high value for frequency, opposite directions, right?
So how do you know it's divide? So frequency, you have to find, so you can divide the speed of light and
By the wavelength.
by the wavelength.
Yeah. The reason I know that is because I always know that the speed of light is always going to be equal to lambda times, right? That's my starting equation.
And it gives you the speed of light. So
Yeah.
Okay.
Yeah. So here we're given the speed of light. It's always constant. It's always going to be the same. Even if I don't give it to you, you know that it's 3.00 times 10 to the 8 meters per second.
Okay.
And then they give us the wavelength. So that means that we need to find the frequency.
Okay.
Okay. Does that make sense?
Yeah.
Oh, maybe. Okay. So I just want to make sure it makes sense. I'm going to ask you about it later. Okay, so my next question is, what happens if I have a question that's looking for the wavelength? Which equation am I going to use in that case?
So frequency equals C under, I mean, speed of light under,
You mean wavelength?
I mean, wavelength.
Wavelength,
Yeah, wavelength equals speed of light under frequency.
that's right. Or speed of light over frequency, right?
Thank you.
Okay. Please skate. So let's go back to the lecture. And you got a free problem out of it. Didn't charge you $80. Don't worry about it. Just give me the book. Okay, I lost her. Okay, so this is the electromagnetic spectrum. So this is going from the very smallest wavelength to the very largest wavelength, right? So if we take a look at the electromagnetic spectrum, we have X-rays, right? Or sorry, gamma rays. So gamma rays are going to be our smallest, right? They're going to have the smallest distance between them. So do you guys, first off, let me take a step back. Do you guys know what a wavelength is? Have anybody been to the beach? Been to the beach. Okay, so a wavelength is, have you ever seen a wave? Okay, so a wave is like this, right?
Yes.
That's a wave. You guys, okay. It's not a pretty wave, but it's a wave. Leave my third grade wave alone. Okay, now the wavelength is going to be either defined as from peak to peak, right? Type that out. Peak to peak. Or trough to trough. Okay, so peak to peak or trough to trough. Okay, you guys know what a trough is? Anybody live on a farm? They live on a farm. Okay, trough is the little bin that you feed your animals in. Like, so if you have a lot of pigs or a lot of cows or everything like that, you throw all the food into a trough, right? And it looks like a little dip like this. So peak to peak would be that, top to top, trough to trough would be that flat part. So it's just the distance right here, this distance. From peak to peak. That's all it is. Okay. Now, gamma rays. Are you guys familiar with gamma rays? Well, you know you want to say it. Go ahead and say it. No. Everybody's familiar with gamma rays. Come on. If you watch Marvel movies, you know what gamma rays are. Nobody watch Marvel movies? Okay, so that's the first problem. See, that's why you guys are struggling in chemistry. You don't watch enough Marvel movies. Go watch
That sounds so.
gamma rays. Okay. Well, that's the Hulk, right? That's the Hulk, exactly. So if you watch The Incredible Hulk, they talk about gamma rays. Well, gamma rays are the rays that make the Incredible Hulk. Now with us, it'll kill us, right? It's not going to make you the Hulk. Okay. So gamma rays or gamma radiation is one of the smallest wavelengths. It's a very, very, very small wavelength. Now, the reason why it's really bad for us is because it destroys our DNA. It shreds into pieces. Why do you think it shreds into pieces? I want to take a guess.
Are they a higher frequency?
I like it. She did this. Okay, so they are a higher frequency. Yes. So they have the highest frequency, the smallest wavelength, because they're inversely proportional. Now, because it's such a small wavelength, it's able to actually emit itself into our cells, right? And to our nucleus, and get to our DNA to do the shredding, right? Now, how many of you guys go to the dentist? Everybody go to the dentist? Okay. Now, the first thing that you do when you go to the dentist, usually they give you x-rays, right? When they give you x-rays, they just go ahead and put the machine on you and go, what's the first thing they do?
They can do like this vest thing to put on.
Yeah, that vest thing is lead, right? It's a lead jacket. That lead jacket prevents the radiation or the x-rays from penetrating your cells, because x-rays can also do the same thing. If you're exposed to them long enough, frequently enough, then x-rays will actually destroy your DNA, right? Okay, so why do you think x-rays do that? Look where it's located at. X-rays. Put on the board here so the people at home can see. X-rays down here. They just got an exam. They all look horrible, don't they? X-rays. What do you think? Come on, you got to talk.
They're close to the gamma rays.
Because they're close to the gamma rays, and the gamma rays does what?
Damage DNA. Why? Because they're shorter.
They're shorter, exactly. So they're small enough so that they're able to penetrate the cell. X-rays are able to penetrate the cell for the same reason. UV light. We use UV light to decontaminate things, right? You know, they used to come in here for a while and they would do all of the tables with UV light, and then they realized that was too much money. So then they start using all this gas, right? So why do you think they use UV light to decontaminate things?
Virus.
To destroy the virus. So in this case, they're hoping that it destroys the virus, because if you look at the size of a virus, it's about the same size as UV light. So what it does, it actually will, on the surface of the virus itself, it fixes the virus so it can't do the things it normally does, right? Because they're about the same size, those rays will actually lock it into place so it won't be able to do what it's supposed to do, right? It'll destroy our cells, because here are our cells. This is the virus cells, right? Virus cell is about 10 to the minus 8, and these are in meters. Our cells are anywhere from about 10 to the minus 5, right? So our cells is what? 1,000 times larger than a virus, okay? So wavelength, very, very small, high frequency. And as we go up, we have X-rays, UV rays, visible light, okay? Infrared light, microwaves, we have radio waves, and we have long range radio waves. And the wavelength gets bigger as we move in this direction, right? And as we move, get bigger wavelength, the frequency gets smaller. Because the frequency is decreasing as the wavelength gets bigger. Because how are they proportional? Are they directly or inversely proportional? inversely. Okay, does that make sense? Okay, so on Monday, you guys actually played with light, right? You guys saw all those different colors, right? They were all at different frequencies, okay? We looked at purple light, bluish purple light, 400 nanometers. We looked at red light, right? You guys saw those red lights, very bright red light, 700 nanometers. Orange is anywhere from like 600 to 650 in that range. Yellow is between 550 and 600. Right? So you saw the different spectrums, right? So those are called, those individual lines were this discrete spectrums. When you look at, or when you guys will be looking at, let's do this right now. Don't worry about it, Hardell, you guys will be doing it tomorrow, so. Don't break my glasses. So, everybody got glasses?
I don't have.
We got, yeah. We got one more. Did yours get a broken one? Put your glasses on. Okay. Now, if you look at the light. Don't look directly at the light. Look to the side of the light. What do you see? Colors. What colors do you see? Rainbows. Rainbows. Okay. Now, white light, visible light. That's what we call visible light. White light. It's actually a whole bunch of colors added together. Right. So when we look at it, normally we just see white light because it's all blended together. But you guys are using diffraction slides, so you can actually see them at different frequencies. So it kind of shifts them so we can actually see all of the different colors. Nice. Okay. Now, again, all of this is energy, right? So we need a way of converting energy based upon the color you see. So red light is going to have a different energy signature than blue light does. So the way that we do that is we use energy is equal to H. Okay, where H is Planck's constant. That's going to be 6 point. Don't worry, it's going to be given to you on the test because is that what you're going to ask me? Times 10 to the minus 34, and it's joules. Joules seconds. Joules times seconds. Okay. So, what is a constant, by the way? Because I keep saying that word constant, constant, constant. If you don't understand what a constant is, it doesn't make any sense. So, okay, let me ask you a personal question. Do you have somebody in your life that's constant? What was that?
It's constantly there all the time. 31 or?
Oh, 34. Oh, because it's cut off. Sorry. It's 34. Sorry.
It's a fixed value.
It is a fixed value. Let me move this over so you guys can see it. Does that help?
It's HU, right?
It's H, new. I have a new pair of shoes. So in other words, the frequency. So we have Planck's constant times frequency is going to equal energy. Now I have a question for you. Since we know that it's a constant value, meaning that it's not going to change, it's always going to be the same value, right? So H is always going to be the same value. So that means my variables are going to be nu and E, right? So what happens if I increase my frequency? So if I go from blue light, which is a frequency of, which is a frequency of 10 to the, it's about a little less than 10 to the 15, right? To a frequency of red light, which is a little more, a little less than 10 to the 15. One is slightly above 10 to the 15. Blue light is slightly above 10 to the 15. And red light is slightly below 10 to the 15. Which one would be more energy? Red light or blue light?
What are the options?
Red or blue?
Blue.
Blue. Why?
It's a shorter wavelength.
It has a shorter wavelength, then that means it has a greater frequency, because we know that frequency times wavelength equals the speed of light, right? So as one goes up, the other, okay? So here you have a shorter wavelength, so your frequency is going to be greater. Here you have a larger wavelength, that means you're going to have a smaller frequency. We know that frequency is directly proportional to light. What do I mean by directly proportional?
They go together.
They go together. As one goes up, the other one goes up, right? So in other words, energy is always going to go up when frequency goes up. Okay, so if I have X-rays compared to microwaves, both are bad for you, right? But which one's going to have more energy associated with it? It's going to be the bigger wall. X-rays, right? That's right. Okay, so I can use this equation. Sit there and calculate energy. Sorry, like shoveling it in my face is delicious. It's rice, beef, beans. Everything is delicious. I've been working on lunch all day. I still haven't finished that part, but I'm like,
I didn't know you
yeah. Oh, I eat everything. From the rooter to the tutor. Let me tell you. Okay. So, how are you guys feeling about this so far? Right? Pretty simple equation, right? It's three letters. Come on, you can't beat 3-letter equations, right? Okay, good. Now I have to get my computer. Okay, so when you guys looked at it, you saw the rainbow. You guys, oh, the rainbow, right? So when you saw the rainbow, that is an example of continuous spectrum. Continuous because all of the lines are running together. They run into each other, right? So line spectrums are when we get those discrete lines, right? Which you guys kind of, so you guys didn't really kind of see. You will see today. You'll see today after the end of lecture, right? You'll see those discrete lines when we sit there and do this experiment. Okay, now what's going to happen is that you're releasing energy. So these electrons are going to be releasing energy because we talked about them being excited. So justice. We already talked about the wave, right? So wavelength from peak to peak, or you had troughs here, don't, well, trough to trough, that's fine. Now, here's a good way of looking at it, okay? So if we take a look at this, here's a bigger wavelength, right? So a much bigger wavelength than this guy, right? So we have two frequencies, two peaks that occur in this time frame, right? So that frequency kind of represents that time frame that we're looking at, where here we have 1, 2, 3, 4 in the time frame, right? So within the same time frame, one set of waves, these waves, you only had 2 waves. This one we have 4. This one has a greater frequency because you have 4 peaks, okay? So when we sit there and disperse white light, we got the rainbow. You guys saw that with your own eyes. Now you get to see it on the screen, right? You guys will see it on Thursday and Friday. When we look at specific elements, every element has a very distinct signature, right? In this case, what we're doing again is we're exciting electrons. We're going to excite electrons. You guys excited electrons on Monday, right? You saw different colors when you put it in the flame. We use thermal energy to excite the electrons. We use electric energy. You guys didn't see a very specific signature, but you will today, I promise. Okay? And so this here is an example of a line spectrum. Okay? This is examples of hydrogen. Now you'll notice hydrogen has 1, 2, 3, 4 lines, right? How many electrons does hydrogen have? Come on, you should know this. It was on the exam. How many electrons? Hydrogen. I got a number. Nope, not 6. How many did you say? 1. How do I know how many electrons does hydrogen have? By looking at the atomic number. What does the atomic number represent? Remember, I told you it all comes back together. You can't get away from it. Atomic number.
1. It's 1.
No, you're right. You're right. It is 1. I'm not arguing with you there. But what does the atomic number represent?
How many protons?
How many?
Protons and electrons.
And it's going to be the number of electrons when the atom is neutral, right? Long as it's
Neutral.
right? Okay, so we have 1 electron. We got 4 lines. How the hell can you explain that? That means 4 different energy signatures, right? We have one that's, if you look at it, it's purple. We have a blue one, we have a yellow one, and we have a red one. Now, this is only within visible light in that range, visible light range. It's only that. We're not seeing the ones that are in the gamma part. We're not seeing the ones that are in the X-ray part. How can you explain that? We have 1 electron. We're exciting that 1 electron. How can I explain that? Do you want to know? I want to know, right? Okay, so let me tell you. We'll get to it. I want you to think about it. Okay, so there's this guy named Bohr, right? Bohr designed this model, right? And he based it upon the hydrogen atom, right? And the model and everything was based solely on the hydrogen atom. Now, Bohr basically came up with a couple of things. He says, we have quantized energy, right? Basically means, remember quantization? It basically means that it's discrete. You have discrete sets of values, discrete lines, discrete energy signatures. How many energy signatures were you able to see for hydrogen? You saw 4 because you have 4 different colored lights, right? Okay, so he said that most of the atom is empty space, which is what everybody was saying at that time, right? They all kind of agreed on that part. Most of it's empty space. That means the electrons are orbiting the nucleus, right? We know that the mass or the density of the nucleus, that's going to be the weight of the nucleus, right? That's going to be signified by what 2 subatomic particles?
Protons and neutrons.
Say it again.
Protons and neutrons.
Protons and neutrons. We know that protons and neutrons make up the mass, right? So we know that the negative charges were the electrons, and they're going to be small and they're going to be orbital, right? So those are the things that he was saying. And he was basically saying that everything that everybody else had said at that point. But the only thing that he was saying different was that this orbiting resulted in quantization, quantized energy. It represented different energy. So you guys saw 4 lines, right? That suggests that there's more than just one place that this electron can go to when it's excited. Okay, so this here, this first step here, right here, that represents that continuous, right? Now, quantize basically means that we have steps. We have steps of energy that we can go up to, right? So in other words, we start off at a low state of the electrons, what we call the ground state, okay? That's going to be the lowest energy level that we have. That's the one that keeps it calm, cool, collected. If you have kids, you know when you feed your kids a whole bunch of candy, what happens? They get hyper, right? So in the case of us giving the electron energy, it's like feeding those kids candy, right? The electron gets hyper, it gets excited. So it's excited to one of these other energy levels. Okay, so this here represents the Bohr's model. So that's the nucleus in the middle. This here, that's your period 1. That's your first period, right? That represents your first energy level. This is your second period. That represents your second energy level. This is your third period. That represents your third energy level. This is your fourth period. This represents the fourth energy level. Now, your electron, you have one electron. It should be, when it's at ground state, it's going to be in that first energy level, right? But if you excite it, it can be jumped up to any of the energy levels. So you'll have some that'll come up to second energy level, right? Depending on how much energy you put into it. Well, some of them are going to go up to the third energy level. Some of them are going to go up to the fourth energy level. Some of them are going to go up to the fifth energy level because it's beyond that, it keeps going, okay? Now, if it goes up that high, it has to release energy that is comparable to the height that it went up to, or the energy level that it went up to. And when it releases that energy, it emits a photon. It emits light. Let there be light, right? Okay. So that jump from one energy level to another energy level, that's called a quantum leap or a quantum jump. Now, the thing about the quantum jump basically says that I can go from ground state to the fourth energy level without passing through individual levels, right? How many of you guys have seen the TV show Quantum Leap? Anybody? No, right? It's on TV now, right? They just started, they rebooted the series, right? It deals with the concept of this guy jumping through time, right? And that's kind of like it's time, space, relativity, all that, right? So the concept of quantum energy, or that quantum leap, says that, let's say, what do you guys, anybody cook for Thanksgiving? What do you cook for Thanksgiving?
Turkey, vegetables.
Okay,
Or,
so let's talk about your turkey, right? Is your turkey good?
oh yeah.
Okay, so in theory, what can happen is that his turkey, where do you live? Turlock. Okay, so he lives in Turlock, California, right? In theory, if we excite his turkey enough, his turkey with the right energy the right frequency with every molecule in there could appear on my table or in my stomach, right? Okay? By me exciting that turkey enough, okay? Now, this has a lot to do with the concept of, you know, teleporters and stuff like that. How many of you guys write sci-fi? Because I know I'm one person. What? Okay, but you guys heard of teleporting? Like, okay, everybody's heard of teleporting, right? Okay, I know this is just so this is that concept of teleporting, right? The fact that we could excite every electron throughout somebody's body to move them from one state to another state and get them to stay there stably, right? That is the concept of teleportation, right? So that's the same concept of quantum energy. You're exciting, in this case, exciting the electron to that next step without having to go through. In other words, he wouldn't have to travel through Turlock to get to Hanford. His turkey could get to Hanford without going through Merced. We have to go to Merced, then I have to go to Madera, then go to Fresno. I wouldn't have to go through all of those. It could just end up on my table without any, okay, without having to travel that full passage, okay? So that is that concept, okay? So you're exciting that electron from one energy level to whatever energy level it ends up at without going through each of the different steps, okay? Are you with me so far? Okay. Now, you guys sort of did that because we're only working with like simple elements. We're not working with a full body, right? Or a full turkey. It gets really complicated when you're trying to do it with a turkey, right? We're working on it. It's a work in progress, okay? So we have the ground state, which is that lowest level possible for that particular electron, to the excited state, okay? So excited electrons are unstable, so eventually they have to come back down to become stable again. Now, when they come back down, they release that energy. They release it as a photon of light. You guys, you look like you want to, well, okay. So here is the picture, right? So this is that same picture I drew for you guys on Monday. Here's my electronic ground state. I put in some energy, put in electricity, I put in heat, I put in some form of energy. It excites the electron to that next energy level, okay? Soon as I excite that electron, we know that it's unstable. It has to come back to stability. It crashes. Crashes, all that energy is released. When that energy is released, we get the emission of a photon, okay? When it goes back down. And so we see light, okay? You guys with me? But I'm using TV shows to push analogies, okay? Now, this here is, again, Bohr's concept. Now, what they found out was that this works great for hydrogen, but it doesn't work so well for helium or nitrogen or oxygen or any other element on the periodic table. Why do you think that's the case?
Because it has one atomic number?
Because it has one electron. Because we're talking about that. Because it has one electron, it worked perfect, right? But as soon as you get to 2 electrons, or 3 electrons, or 4 electrons, it gets complicated, right? And it doesn't hold up, okay? Because the electrons, they play off of each other, right? And so what they determined was that they actually had to use what they call a set of 4 numbers, right? We call them the quantum numbers, right? There are 4 of them. The very first one is called the principal quantum number, okay? Now, the principal quantum number represents those energy levels that we talked about. We also call them our periods on our periodic table, okay? So then after that principal energy level, right, we have a sublevel. Now, the sublevel is going to be kind of the orbit pattern that it takes. Then we have what we call the orbital. So each sublevel has orbitals that are going to be associated with it. And then we have the number of electrons that are in those orbitals. In other words, we have to have one that's going to be spinning one way and one that's going to be spinning the other. Let me elaborate a little bit, right? So that principal energy level, these are going to be our periods. Those sublevels, that's going to be kind of like the shape that it takes that the electron travels, okay? Now, we have, as of right now, we have four of them. We have the S, we have the P, we have the D, and we have the F. Now, in theory, we can have more than that. After F, you can go to G, H, and I. But we're going to be limited by the periodic table, what we know right now. So we're only going to go to F. Okay. So, and then we have orbitals within these sublevels. Well, the S sublevel has one orbital. The P has 3 orbitals. The D has 5 orbitals. And the F has 7 orbitals. So if I had a G sublevel, how many orbitals would it have?
9.
9. Now, each orbital, so good. Each orbital can hold 2 electrons. Okay. Okay, so each orbital can hold 2 electrons. So then the S can hold, what is the maximum number that the S can hold? Number of electrons.
2.
Okay. The P. The D.
F.
The F.
14.
And if there was a G. Okay. Okay, so watch your periodic table. So I said the S can hold how many again?
2.
2 electrons, right? Okay, so this here represents our S. P can hold how many? 6 electrons. 3 orbitals, it has 6 electrons. 6 electrons. The D,
10.
10. And the F,
14.
14. Okay, so if we look at here where I drew the S at, that's 1, 2. If we look where I drew the P at, P looks like 6, 6, that's supposed to be P. Okay, that's 1, 2, 3, 4, 5, 6. If we look where I drew the D at, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now where I drew the F at, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now these two actually belong in the d orbital. They're just kind of placeholders. Okay. So the way that the periodic table really looks, I'm going to expand it and then I'll bring it back in so you guys can see. It really should look like this, but they make it so that we can fit it on an 8 by 10 piece of paper. So that we can actually print it out and look at it. So here, this is where that F is at. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can see that these guys are actually in the d orbital. Okay? Are you guys with me? Yeah. Good. So we're going to talk about electron configuration, right? So remember I talked to you guys about quantum numbers. Now, quantum numbers are set up for every electron in an atom. So if we have one atom, we're looking at one atom, and the atom has 8 electrons. Those 8 electrons will not have the same quantum numbers. They will have a different set of quantum numbers for each electron that's there. You guys don't have to worry about the quantum numbers, but instead you guys are going to have to worry about electron configuration because it's going to help us understand valency. We've talked about valency already, but we're going to talk about it in the context of electron. Okay, you guys with me? So let me make this normal again so that it looks like a periodic table you guys see. Okay, so we have this guy, it's all nice and set up for us. Reach this part here. Now, when we talk about electron configuration, we're just basically letting us know where the electrons are at because we need to know where they're at and whether or not they're going to be able to react with things. They're going to be given away or they're going to be taken and all that stuff. Okay, so we're going to start very simple. We know that hydrogen has how many electrons? 1. So the way that we would write hydrogen electron configuration, we'll look here, it's over here in the S, right? And helium, technically for this case, this guy really should be over here as well. So it should be drawn technically over here. Okay. So hydrogen, its electron configuration is going to be it has 1 electron, so we'll draw this H, colon, and then we'll draw 1, and then we write S, because it's the S sublevel, and there's only 1 electron there. So 1s1. That will be its electron configuration. So we've talked about where that electron is located in hydrogen. So let's say I have carbon. Carbon. We always start at that very first electron because carbon has a total of how many electrons? So we should account for 6 electrons. So we're always going to start. One is going to be here in the 1s, right? Actually, we're going to have 2 because how many electrons can the s orbital hold?
2.
So we're going to write 1s, 2. So that accounts for 2 of the electrons. And then we go down here. We know that carbon is located at that spot. Okay, so then we'll go, that accounts for those 2 electrons initially. Then here we have 2. We look at the period.
2s2.
It's 2. So it's 2 s, and we know s holds how many again? 2. So then that accounts for those electrons. And then we have 2 more, right? And those are in the p. So then it's 2p.
2.
Okay, so then that accounts for those 2 electrons. Okay, are you guys with me so far?
Yes.
Okay, so let's see if we can do something that's a little more challenging. So when we get down, let's say, there are a couple of things that I need to tell you. So the organization is based upon energy, right? If you kind of take a look at the periodic table, it's also based upon energy. Hydrogen had the lowest amount of energy. Okay, that's period 1, right? And then each of these periods represents a different energy level, right? So these numbers here are going to represent our principal quantum numbers. Okay. So when we get down to period 4, right? The S is going to be at period 4, but the D is going to actually start at 3D. Now, the reason why this occurs, it has to do with what they call degeneracy. And I'll show you a figure that kind of help explain it a little bit more, but it's based upon energy. 4S is a little lower in energy than the 3D orbital. So you're always going to be putting the electrons in a way that it's in the lowest energy level possible, because we want to keep a low energy level. Does that make sense? In other words, electrons are lazy, okay? They don't want to use a lot of energy. Or S is going to be lower than the 3D in energy. So it's going to fill up that one first, okay? And then it'll continue over here with the 4P. Okay, so it'll go, if we're talking about iron in this case, we'll write symbol for iron, Fe. We always start at the first period. So it's 1, and how many can be held in that s orbital, or 1?
2.
2 electrons. So that accounts for these. Okay, then we go to the second period, and we start with 2s. 2s. How many can be held in the s orbital? 2. 2. So that's 2. Then we come over to here. This is the p. So how many can we hold in the p? How many? 6. So 2p6. Then we go to the next period. How many ES? 2. 3s2. And over here, this is the 3p. How many are the 3p? 3p6. Then we have the 4s. How many in 4s? 4s2. Then we have 3d. Okay. And then we count over to the point where we're at. That's 1, 2, 3, 4, 5, 6. So 3d, 6. Okay.
Dr. Henry, can you also just write the AR to skip doing all that and then just start at the 4S?
Okay, don't steal my thunder.
Oh.
So yes, technically you could do that. We'll talk about how to do that here in a second. So this is the long way of doing it, right? And so you'll often see a lot of times on tests, they'll give you the long way, right? Okay, now there is a short way of doing it this way, right? Since you already stole my thunder, I was gonna make you really the hard one first. For the long way so you can really appreciate it, right? But now you messed it up. Okay, so let me show you the short way, okay? Now the short way is using the noble gas, right? You start off with the noble gas. The noble gas acts like a core. So how many of you guys have a checking account and a savings account? You have them both, right?
Yes.
Okay, what is your savings account for?
Emergencies.
Emergency, or to save, right? So are you supposed to touch your savings account?
No.
Unless it's an emergency, right? So you're not supposed to be touching your savings account, okay? Now, what we're gonna do is we're kind of setting it up the same way with our electrons. So the electrons that are in our core, those are the ones that we wanna save. We don't wanna touch those, right? Those can't be used for anything, right? Except for emergencies, okay? Now, the other ones are kind of like in our checking account, okay? So your core is always going to be your noble gas. So you always want to find a noble gas that will be before this. So if we're talking about iron, we're going to write Fe colon, and then we'd write bracket. And we write bracket, the noble gas that would be right before iron. So that would be argon. And then you write the things that would follow it. Then it's the 4s, 2.
Sorry, do you mind starting that process one more time?
Sure. So let's say we're talking again about iron, right? So what you want to do, you want to find a noble gas that's before
Oh, okay.
argon. So that's the one that we're going to put in brackets. So we're going to put the noble gas that is right before the element that we're looking at. And then we go through the process normally. It's 4s. How many?
Okay, so that same line after the noble gas, then you add to it.
So you're pretty much simplifying the whole process?
Yes.
Yes.
Oh. But it can only be done with noble gases?
That's right. Only with noble gases. That's correct. All the right questions. Okay. So we take that noble gas, and then we have 4s2, and then 3,6, and that's it. Now compare the two. Right? Which one is easier?
Noble gas.
Okay. And so it also lets us know which electrons are available to play with, right? These 8 electrons here are going to be available to play with because there's 2 in the s orbital and there's 6 in the d orbital. We can play with those. The rest of the electrons, they're locked up in a ball. We don't want to touch those. Now, those are only in the case of emergencies. Right? Okay?
Sorry, can I ask you one more question? I know you might have gone over it, but I probably missed it. So why is it 3D instead of 4D?
It's 3D because the 3D is actually a higher energy level than the 4S. So they dropped this level down here and they realized that it's actually a higher energy level. So we have to do the 4S first before we do the 3D. So it has to be energy, right? And then the same thing happens down here with the F. So this will actually start at the 4F, right? So normally this is at 6. So F is dropping down by 2. Somebody's at your doorbell.
Sorry.
Right. Hopefully it's pizza. Save me a slice. Yeah, I can't get enough food if you can't tell. After being sick, you want to eat everything. Okay, questions? I have like 5 people. So it's period, letter of group. Yes. So the way it's organized, it's the period, it's the level, the sublevel, and then the number of electrons that are going to be in that sublevel. Right? We always know that the S has how many electrons? How many?
2.
Yeah, so we can't have more than 2. We can never have more than 2. On multiple choice tests, the first thing that you always want to look at is look what you have. If you have S6, right? You say you have one S6. Is that going to be correct? Yeah, right? First thing to look at, okay? Now, you can have less than less than 2 electrons in the s orbital, right? Because we know that with hydrogen we have 1, right? So it's 1s1, right? But you're always going to fill it in order because you always want to go low energy to high energy. So now that you guys know that it goes from low energy to high energy, is the S lower in energy or higher in energy than the P? Than the P. The P is going to be higher. That's right. Because we fill it in later, right? Okay. Do you guys want to do one more? Or do you think you got it? I got it. Problem.
One more, please.
One more, please. Okay, we'll do one of the problems then. It'll be kind of like this. So we'll go to active learning. Problem number. So you guys can see stuff. Everybody has their periodic table available? We'll take one after this question. Are you holding it in? Oh, I've been there. Let's do number 13. Oh, we're gonna do it the hard way, the long way. And then we'll do it the short way. Okay. So you guys are gonna have to help me. I don't know anything. I'm a newbie. So we're doing for copper. So it's going to be what? Copper. Copper. So where do I start at? 1. Oops.
1F.
1S.
2.
2. Then?
And then 2s2.
2.
And then 2p6.
2p6. 2p6. Oh. There's delete. 2p6. There we go. Then 3s2. And then
3P6.
And then we're back at P, 3p6.
Mm-hmm.
And then
And then 4s2.
In this case, you'd put 3D10, no? First?
okay.
Huh?
Spoiling my stuff. Man. So our first.
Well, that's to help you like you didn't know.
I know. Okay.
Well, as I'm writing it down, yeah, I was looking, I'm like, wait, the 4, and then there's a 3, shouldn't, okay.
For us,
That's confusing.
and then we would say 3D8, right? Or 3D9.
3D9.
9, yes. So our first instinct is to say 3D9, right? So now what happens is that when it's so close to filling that d orbital, right? It's 9. It needs one more to get it completely filled. The energies are so close together, it's actually lower in energy to fill up that d, because it will be more stable than to put 1 in that 4s, to keep just 1 in the 4s. So really what it does 3D10. And then
We take
take it from that 4s. So you'll have 4s1.
4s1. Do we have to move? Do we have to move them?
Yeah.
Before,
What do you mean? Do I have to move them?
like 3p6 and then 3d10 and then back to 4s1.
No, because it's more stable for all of the other ones that are below it to say normal. So that 4s, remember I told you that 4s is a little lower in energy, right?
Oh, yes. Yes, that's right.
Close. They're really so close together. It's just a little bit lower in than the 3D, right? So, but it's more stable for it to fill up that last one. Okay, so this here is an exception. Okay, so this is one of those exceptions. So if you have 9 electrons in the d orbital, it'll prefer pushing it over to 10. So that's the same thing that happens with silver. That is the same thing that happens with gold.
Dr. Henry, so when does the D go before the S? Because I was reading on forums that sometimes it's incorrect this way and that the D has to come first.
Yeah, because it's not.
Well, this would be an example where the D comes first, right? Because it's so close. So it comes first when it deals with filling that last orbital, because they like to run in pairs. Because how many electrons are in an orbital? 2. Right? So
2.
that's right, 2. That's right. So since there's 2, right? So it would prefer filling up that d orbital completely, because it's at 9. It needs one more to make it completely stable, right?
Yeah.
First stabilizing that one first before going to the S. So this would be one example where the D would come first. Does that make sense?
Yeah.
Okay. I'll tell you when you hit submit, you should get the correct answer. Did it work for you? Okay. Bathroom break, and then we'll come back and then we'll start over. So we'll give you guys 10 minutes. Go pee, go Go brush your teeth. Go find your girlfriend.
Go eat your slice of pizza.
Oh, yes. Send me my slice of pizza. Yeah. Okay. So I'll see you guys back here at 10. A lot of messages. This is good. I like it. A lot of messages. Good job.
Oh, that's fine.
So Yolanda, to answer your question about silver. It says it's wrong. Go fight.
Real quick, can you explain one more time why you got 4S1 and 10?
Because it's so close to being right. I mean, so close to being
10. Use the S automatically equals 1 and then use the 10.
So it steals it from the S. So it actually takes it up to the S so that that 9 will be completely full.
Oh, because we're 1 off the 10. That makes sense. Okay.
So S, 2S, 3S2. Yes. Question. Okay. What are you buying? I said, what are you buying? I said, you're shopping.
Dr. Henry,
Yes.
do you mind going, while we're on break, do you mind going back to the sub-levels on the periodic table? Like where they go? I might have missed that.
Okay, so right here, 1 and 2. Group 1 and 2, that's going to be your S.
Okay.
Team. P. Group 3 to 12, that's going to be our D. And here.
Yeah. F, right?
7 is 7. 71 is actually part of the D. 71 and 103 are all part of the D.
Someone find me.
So, and then here, the D is going to start at 3D. So even though it's on the 4th period, it's really 3D. And then down here, this is going to be the 4F. It's actually going to start at the 4F. Even though it's on the 6th period.
So wait a minute. So where's the F? Okay, I see.
It looks like a 5. It's an S. And then you think about it. S holds 2 electrons. 1, 2. P holds 1, 2, 3, 4, 5, 6. D holds 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Question for period 7, would that be considered 5F?
No, period 7 is going to be 7S, and then we go to 5F down here.
Yeah, that one. That's what I meant.
5F, yes, it's 5F, and then that would be 6D. This right here would be 6D. Yeah. 6D, and then this here would be 7P.
I just won. Like I did one comment. I just want to see group again.
Who you are?
Yeah, that's what I was like. Anybody comment? So I can't.
Oh my God.
So another question, where do you get the other ones, G and H whenever you have finals?
So those are hypothetical because we don't have enough elements for them yet, but we have the ability for the periodic table to grow, right? So like when I was in college, we were right here.
Oh, wow, that's cool.
It's
Oh, I had an idea.
it was these two where we were at. So now we've added these ones as well, right? And so
I wish it's better.
we made a lot of progress. We're going to be making more progress.
Okay, that's great. Thank you. That's awesome. Good.
So like G and H are going to be coming later on, but it's just theoretically. If there was a G and H, then
Oh yeah, I know. Like
figure out how to get. Yeah.
Oh, no, not really.
so they threw no hitter to you.
No, we had, we scored 2 rounds, but they scored 4. That's just.
Oh, yeah. Yeah.
That makes sense without too many comments. So that's what you said. Kept running. Our coach gets mad very.
You guys want to try one more?
Or your pictures? Let's do one. Just like your pictures.
Let's do one just like the last one.
It's one more.
Yeah, we lost last time.
Just try coach do like an hour with pictures before you practice.
Yeah.
So
That's
I should also tell you this. When
just
you're
like
in this area, meaning that you have four electrons in the D, right? It's going to actually steal from the S again too, right? Because it likes to have at least one in each orbital in that case. Okay, so if you're at 9 or if you're at 4, you're stealing from the D. Okay, 9 and 4, you're stealing from the D. I'll repeat that again. 9 and 4, you're stealing from the D. So if you have 9 electrons in the D, you have 4 electrons in the D. Sorry, you're stealing from the S, not the D. You're stealing from the S. Okay, 9 and 4, you're stealing from the S. Okay. Okay, you guys ready? Ready to try one? Okay, so let's see. Okay. Everybody's got in the habit of bringing their periodic table, right? Okay. Let's do let's do this one. Actually, no, let's see. There has to be another. Chromium. That one. Let's do that. Now, this is the way that we're doing it. It's called the condense or the noble gas electron configuration. So you're using the noble gas as our core. Okay, so where am I going to start at? What's going to be my core? Okay, so we have chromium, we go back, we see argon is the noble gas before chromium. Okay, so we have argon, and then
you have 3d5 or 4s2, I guess.
4s2. And then
3d6.
Now we're doing chromium.
Oh, 5. Sorry.
4, isn't it 4? 1, 2, 3, 4.
Okay, it's going to be 4, okay? So what we know, I just said, what did I just say? Can I scoop that up?
4, 9, and 4 stealing from the S.
Okay, so is this a 4?
Yeah.
So we're going to be stealing from the S. So if we're stealing from the S, we're going to leave 1 in the S. And then we're going to have how many in the D? The 3D.
About 5.
Okay. Your phone. Free homework assignment. Come on. Is it right? Is it wrong? Oops. Actually,
Yeah. It's
yeah.
same thing. The same thing.
It's habit because you're just like.
It's 5.
Yeah.
You want to click it?
How do you know when to steal?
Yeah, that was going to be my question again. Can you repeat the 9 and the 4 stealing from the S?
Yes. So when you have, if you go ahead and do it like you're doing it normally, if you have 4 electrons in the d orbital, right? Or if you have 9 electrons in the d orbital, I mean d subshell, d sublevel, sorry, sublevel, in the d sublevel, then you're going to take from the S, you're going to take 1 from the S to fill the d sublevel. So let me explain to you what's happening in a different way.
So is it between 4 and 9? So any, or is it only 4 and 9?
It's only.
But 4 looks like it's like it's not an odd, like the 9 is, it's not an even number. The 4 is an even number. That's what's throwing me off.
Okay,
So
so
it has to be in the middle, right? So 10, full potential, or in the middle?
let me explain. I'll explain to you, and it'll make a lot more sense. So here, this represents the 3D. Okay, so we're saying we're in the 3D right now. So this is what we're looking at. Now here, this is going to be our 4S. Now in terms of energy level, this here represents an energy diagram. 4S. Okay. Now these guys are really close in terms of energy. So this is energy, right? Now, what they've determined is that if we have electrons, what they'll do is they'll actually go through and they'll fill, they typically go through and fill the lower energy first. Now, the way it works is that they'll go in and they'll put, this here represents electron, okay? And we have one that would be in a positive state, right? Now, normally, it would come here and fill the S completely first, right? But now what it will do is these guys, they'll put them almost at the same level. So it won't fill it completely first. It'll act like they're all at the same level. And it'll come here and then put the other electrons. But only for this situation, right? Because it's a lot more stable for it to have one electron in all of the orbitals rather than having one that's going to be paired down. Okay, it allows it to be more stable. Okay, now when there's 9 electrons total, right, in the orbital, so what it'll do in this case, again, it'll come in, it'll put the first one here, and then it'll go ahead and fill this guy up completely, because again, it's a lot stabler for it to have these guys all paired up and full than having that one over here and leaving that odd one out. Does that make sense?
Yes.
Okay. So let me show you one more thing. I'm going to draw this whole thing for this one for chromium. Take these off. Okay, so when the electrons are being loaded in, you're always going to have one that comes up and you're always going to have one that goes down. Okay. And it's going to start with the lowest energy level first. Then when you come here to your P's, it's going to go and place them all in the same orientation, each one in different orbitals. And then it comes back and then put these guys in. Okay. You guys see that?
Oh, okay.
Okay. So it first goes up, puts these all in the same orientation, and then it'll come back and start filling up the rest. Okay. Okay. Let's see, there are a couple of questions. Okay, so how are you guys feeling so far? Good? Excellent. So let's see if we can make it a little bit harder. Okay.
Hey, Dr. Can you spare periodic table on you?
Probably. Fine. I'll lend it to you. It's going to cost you.
All right.
Yeah, $1 there. So, let's see. Periodic table. So now we're back at the periodic table. So you guys remember what ions are, right? What are ions? Now, don't all you guys yell at me at once. You guys just talk so much. Can't get you to shut up.
It's an atom with a charge.
Okay, it's an atom with a charge. Okay, so let's say we have, manganese. So we're going to do manganese. Okay, and then we're going to talk about manganese 2+. Write that down here, manganese 2+. Okay, now I want you to do it the condensed way with the noble gas core. Save us a little. Okay, where am I going to start at? Okay, we're going to start from argon. Okay, and then
fluorescent or fluorescent.
And then (3D5). Okay, so that would be manganese. Now, if we lost 2 electrons, when you lose 2 electrons, you're always going to take away from the outer shell, or what we call the higher period. Okay, now we have a 4s2 and a 3d5. Who are we going to be taking away from?
4s.
We're going to take away from the 4s. So in this case, for the magnesium 2+, that's just going to be.
Wait, say that again. When it's a plus, we take away from the what?
Outer shell or the higher period. So if our period, we're looking at our periods here, right? We have a 4 and a 3. Which one is higher? The 4. So we're going to take away from the 4 first, and then if we still take away from stuff, then we'll go to the 3. Does that make sense? So then in this case, the answer would be argon 3D5. Okay? Because you take away from the higher period first.
Okay, the higher period on the periodic table where they're labeled 1, 2, 3, 4, 5, 6, 7.
That is correct, yes.
Okay.
Okay, now you're asking me why, right? Okay, that's a very good question. So where's the nucleus located at? Yeah. In the center, right? So we have the nucleus in the center. Now, period 1 is right next to the nucleus, right? Period 2 is right here, right? It's right after period 1. Then period 3, then period 4, then period 5. Okay, so you guys can't see. Maybe you can't see. Look at my picture. Let me pin myself. Hold on. Stop sharing. 1 second. I'm gonna figure why everything is not right. Stop sharing. And okay, so center, right? And then so we have the outer shell, right? Then we have the next level, the next period, the next period, the next period, the next period, right? So this here represents that first period, this represents the second, this represents the third. Okay. Now, if you're taking away electrons, are you going to take away the one nearest to the nucleus? Is that going to be the easiest one to take away from? Or are you going to take away the one that's way out here on the outside? Way out there. Okay.
The outside.
Let me give you another analogy, right? So let's say you have a mother, right? And you had a mother who has a single child in her hands. Or you have a mother who has 20 kids, right? One that's really close to her and all the rest are just like way out, right? Which one are you going to steal a child from? The mother with the single child that has them right next to them, or the mother that has the 20 kids? The one with the 20 kids, right? And you're going to take the one that's furthest away from the mom, right? Because a mom is going to be very protective. If you take the one that's closest to the mom, what's going to happen? She's going to fight you, right? Oh, hell no, you're not taking my kid, right? Although my mom would say, here, take him. Take him. You'll be given back in a week. He has too many damn questions. Why is the sky green, you know, or blue? Okay, now it deals with energy, right? It's going to take more energy to take away the child from the mother that's in her arms than to take the one that's, you know, running across town, right? Okay, so it's the same concept. It's easier to take away from that outer shell than to take away from the ones that are closest. Does that make sense? Okay. What did you learn in chemistry today? How to kidnap children. Okay, so let's see if you guys can do this, right? Let's say we have let's do nickel 3+. I'm going to do it the short way, or the condensed, or noble gas core. Okay, so I see that we're starting off with argon. You guys agree?
Yes.
Okay, and then
4s2.
sure. If we're doing nickel, yes, we have 4s2. But are we doing nickel or are we doing nickel 3 plus?
I got 3d7.
3d7? So 3d7. Okay, so you're right. If we were doing nickel, it'd be Ni, right? Then we put our argon. And then we have argon. Four S2, 3D8. And then as you take it away, you take it away first from the 4S and then the 5th. Okay? Questions? Okay, let's do a homework problem. Let's see, number 30 to 32. Where are we starting? We're going to start with argon, our double gas. That's right before it. Okay, and then 4S. No? Okay. Right now, what you telling me right now? Yes. You said I saw D, but what? You said 3? 3D? Okay, so 3D, 3D2. Okay? You guys think? Is that right?
Yes. Yes.
Okay, plug it in. You tell me if it's right.
Yes.
Okay. Piece of cake.
Dr. Henry, can we do one with valence?
Can we talk about valence?
Yeah.
Yeah, we can. So actually, let's do one where we add electrons, right? So let's do, let me give you guys an example first, and then we'll come over here and do one of the problems over here. And then we'll talk about valence, okay? But actually, we can talk about valence here, the one that we just did. So let's see, go back to the problem. So here, although it's transitional metals, when you talk about valence, you're talking about the ones that you could actually react with, the electrons that you could use for a reaction. So in this case, we would have 2 electrons that would be available to be involved in the reaction, right? All the electrons that are in the core, that in that argon, they're safe, right? They are not going to be used. The only time they're ever used is if you put a lot of energy in, right? So it has to be like an emergency cases, right? Just like your savings, okay? So this guy would represent our valence electrons, sort of, for transitional metals, okay? Now we'll talk about normal transition, normal valency when we talk about the main group of consent, okay? But before we do that, let's talk about the idea. So let's say we have Tellurium. 2 minus. So how would I do this? Okay, so we start with argon. Are you sure argon?
Krypton or krypton.
Okay, so we'll start off with krypton. So we have Kr. Okay, and then starting off right here. What's next? That's right. So we have S5 or 5S, sorry.
Oh, wait. Yeah.
5S.
5S2.
Okay, I know it looks like 5, 5S2. 5S2.
That's 4D10.
4D10. That's right. Because remember, it's going to increase. 4D10. And then
5P4.
5P4.
Are you sure? 5P4? Because this means we're adding how many electrons?
5P2. Oh, wait, no, I got the other way around.
5P6. Yeah.
5P6.
That was complicated.
Okay. So, yes, that would be correct. Or I could have also just said tellurium 2 minus. And then I could have done bracket. Excellent.
Because you added it.
Yeah, I added 2 more, so then I have that noble gas. So on an exam, either one would be acceptable. I don't know about Chem 101.
Dr. Henry, I have a question. If you didn't have the negative charge,
yes,
could you still write XE and then show the +2?
No.
Okay.
No, if there wasn't a negative charge, the reason why it's XE is because if there's a negative charge.
Right. I was just saying if you could do it backwards.
No, you can't do it backwards.
So when we always add 2, can we go to that element? Does that make sense or no? So say like for,
well, if we had, let's say for instance, we had TE1, you can't go to that element. You only can go to noble gases.
okay.
Noble gases are the only ones that can go in the brackets.
Oh, okay.
Okay.
Oh, that makes sense. Okay.
Because they're stable, right? You're setting up a core. Okay. Make sense? Okay. Okay, so let's see about a problem, then we'll go back to the lecture, and I promise you we'll get to valence. Okay, so number, so let's try 20, 22. This one isn't, there isn't a noble gas. So got to do it the hard way. So where am I starting at?
1S.
1S.
1S2.
1S2. Okay. Then
Question.
2s2, and then so we did 2s2, 2, oops, said p, d6, and then
3D. Yeah, 3D.
periodic table.
3s2.
3s2.
3s2, and then
3p.
3p6. That is correct. Okay. So in this case, you could put brackets argon. Yes.
Okay.
But not in this case because they're not accepted, right? I don't have that option. On the exam, you can do that. I would say. Okay, questions? Concerns? Cash?
So for this one, it went all the way to 6 because of the 2 negative?
That's right. We're adding 2 more electrons. That is correct.
And you couldn't write it as like on a test, not on this
Yeah.
one, as
Write it as argon. That is correct.
you could?
Yes. I
Okay.
would on the test, yes.
Okay.
Any questions? No other questions? How about cash? Okay. Okay, so let's move forward. Now that I gave you guys some previews. Okay. So this is just basically letting us know in terms of energy levels. 1 is going to be the lowest energy level, 2, 3, 4, 5, all the way up to 6. And we already know that that principal quantum number, right, is always going to be that period that we're talking about. We've already talked about the S, the P, the D, and the F sublevels. You guys are familiar. How many electrons can be held in the S? How many in the P? The D? And the F? Okay, and if there was a G?
60? 18.
18. Okay. Okay, when we talk about those sublevels, S is always going to be lower in energy than the P. Okay. So, and then if we talked about the S, the P, and the D, the S is going to be lower than the P, which is going to be lower than the D. Make sense? In terms of energy. Okay, this is just basically showing you those energy levels, right? Here's the 3S, here's the 3P, all the way up here is the 4D. You notice, I mean, the 3D. You notice the 4S is slightly below the 3D. So we talked about the number of orbitals. The S has how many orbitals? The P Okay, you can read the screen. I don't have to tell you. Okay. So now again, these orbitals, it's three-dimensional, right? So let me show you what they look like. So this here is just basically showing you how the electron orbits the nucleus. Okay. So Bohr thought it looked like this, that it just simply orbited naturally. Well, that kind of works out for the hydrogen atom, but it didn't work out for all of the others. So in reality, they're all kind of that density. They're spaced out. You have them going in so many different directions. Let me show you what it looks like in each of the different sublevels. So this here represents the S, right? This is the first orbital. We call it PX, right? Because it's on the X plane. So that's the first orbital. So it looks like barbells, right? This is our PY, and this is our PV. So those are your three orbitals for the P. This is the one for the S. And then this one is for the D. And the F, it is very complicated. We don't have it here, so you only get up to the D. Okay. So these are the 5 for the D. And there will be 7 for the F. Now, the 1s can be encompassed by the 2s, which can be encompassed by the 3s. So in other words, as we increase the energy, the atom is also going to be increasing. So this represents where the electrons are going to be orbiting around, right? So who's going to be our biggest atom based upon this? 3s. 3s would have our biggest atom. So if we look on our periodic table, who is going to be our biggest atom if we're looking at group 1? Who?
Francium?
Francium, yes. Francium is going to have the biggest butt. So it's going to be the biggest atom. It has more shells into it. Have you guys seen the Russian dolls? I don't know what they're called.
Yes, the ones that have a big one, a little one, they keep on going smaller and smaller and smaller.
Exactly, yes.
Yeah, I have one.
Excellent. I need to buy a couple, so to bring in for class. You guys can appreciate it, right? So that 1s is the smallest little doll in there, right? Then you have the 2s, that's just a little bit bigger. So that's the way it works. Your biggest doll is big, right? Because you have a shell added onto it. That's the same thing that's happening with these atoms. Okay? As we go down the periodic table, they're going to get bigger.
Dr. Henry, doesn't the mass number represent that as well in numerical form?
No, because, for instance, if we take a look on your periodic table and you have, let's see, our best example is your copper and your nickel, right? So if we look at the atomic mass of copper and nickel, which one is greater? I mean, not copper, cobalt and nickel, not copper. Cobalt and nickel.
Oh, the cobalt's bigger.
The cobalt is bigger, right? And so there's another case, but I can't think of it at the top of my head. But that's the more known case where you have one that has a smaller atomic number that is greater, heavier than the one that has a greater atomic number. But what we do know is that as we go from left to right, as we move from left to right on the periodic table, let me pull my periodic table. Talk about this again. So again. So as I go in this direction, from left to right, as we go from left to right, the atom actually gets smaller. Why do you guys think the atom gets smaller? It makes sense that it gets bigger. It gets bigger when we go from top to bottom, right? That makes sense because you're adding layers, right? Why do you think it gets smaller as we go from left to right? Say it again. What? What?
What gets smaller?
The atom, the size of the atom.
Okay, I thought you said that. I was like, I thought it got bigger.
No, it actually gets smaller as we go from left to right. It gets bigger as we go from top to bottom. The atom gets smaller because more atoms.
So is it because you're adding layers? In this case, you're removing layers?
No, no. Let's break it down, right? So we know that what is the difference between, as I move from left to right, let's say for instance, it's helium and hydrogen and helium, right? What are we doing?
You're adding a proton?
We're adding a proton and we're adding an
electron?
Electron. So we're adding a proton and an electron. So what's happening is that the electron is circling the proton, right? And I also told you guys that the electron weighs significantly less than the proton. Protons are located in the center. So what happens is that the proton attracts the electrons closer to it because you have two protons. So it's going to be pulling those two electrons closer because there's two protons in the middle. So as we move from left to right, we're increasing the number of protons. So we're pulling everything closer because they're orbiting. They're also lighter, so they're going to have less pull to them, so they're going to get pulled in closer. Okay? So as we move from left to right, it's going to get smaller. As we move from top to bottom, it's going to get bigger. Okay? In terms of size. Okay?
Does this play any correlation to the wavelength?
Does it play any correlation to the wavelength? No, because the wavelengths are going to vary depending on the electron and that's being excited. So you have multiple electrons that are going to be excited. So you guys will notice that you'll have multiple lines that you're going to be seeing in certain cases.
Oh, okay.
We'll talk about it. You guys will see it tomorrow or on Friday. So. If I don't forget. Okay. So, Pauli exclusion principle. The Pauli exclusion principle basically says that there can only be no more than two electrons occupying the same orbital. So you can either have 0, 1, or 2. That's it. So in other words, an orbital, which holds how many electrons? 2, right? It can only maximally hold 2. And how many orbitals are in the P? 3. That's right. Each one holding how many? 2 electrons. So that's a total of 6. Okay. So you guys have already learned electron configuration, so I don't need to talk to you guys about it again. Okay. This is just showing you what we just talked about, right? That order. So this is just showing you what the electron density looks like for this particular subshell. So this one's probably the one with the donut in the middle and this one at the top. So this is just verifying, showing you how to write it. Right? So the principal number, the sub-level, and the number of electrons that are there. This is giving you the electron configuration for the first view. We've talked about the core, right? The noble gas core. You guys already know how to write the electron configuration. You've already done some of these examples. We also talked about those exceptions, right? What are the two exceptions? When we have how many is the d orbital?
4 or 9.
4 or 9. Okay, so now we get to talk about valence, right? So valence is when we're looking at the s and the p orbital. So this is what actual valence means. So remember, when we're talking about transitional metals, their valence is going to be different. So if we're looking at the s and the p orbital, we just add the numbers that are in the s and the p orbitals. So for instance, of that outer shell. So if we go to our periodic table, where's the s going to be located at again? Which groups? Which groups? The s. Which groups? Oh, 1 and 2. Right here, right? That's going to be the s, right? And the p is going to be where? It's going to be here, in the middle, here, where this peak is at, or is it going to be?
Group 14 to 18.
14 to 18. Don't forget the groups, right? So group 14 to 18, so that's going to be the peak. So when we talk about valence electrons, we're going to be looking at the s and the p. So for instance, carbon has how many valence electrons? How many do we have? We're talking about carbon.
Six.
Are you sure? We have 6 electrons. How many valence electrons? Okay, what is the electron configuration for carbon? Let's do this short way. Just make sure. Carbon, it would be what? What would be the noble gas in brackets?
Helium.
And then?
2s2.
2s2.
So it has 4 valence?
We'll have 4 valence, that is correct. But what is the last part of the electron configuration?
2p2. 2p2.
Okay, so the 2 electrons that are in helium, right? That's those are not going to be touched. Those are saved. So valence electrons are the electrons that can be used for reactions. So that's going to be the 2 that are in the s here and the 2 that are in the p. So we're always looking at that outer shell. So in the case for carbon, the outer shell is going to be, or the outer level is going to be the 2. So there's going to be 1, 2, 3, 4. So that's why I told you earlier, you can sit there and count to determine how many electrons there are valence. Okay. So in the case of antimony, how many valence electrons does antimony have? What is the symbol for antimony? SB. Okay, so it's SB. So, how many valence electrons?
5.
Okay, so we just count the S and the P. So there's a total of 5. So that's 1, 2, 3, 4, 5. So it has 5 valence electrons. Okay. So those are the electrons that can be used for reacting. It won't touch this, even though technically the 4D, the 4D is available, it's not going to touch it because it's in the 4 orbital, right? So it'll touch these first. It'll mess with these. It'll only use this under emergency conditions. So we only look at the S and the P when we talk about valency. Okay, that's why those transitional metals They had their own special way of doing it.
So that's one for valence electrons with S.
The S and the P. Okay, so for instance, if I have barium, how many valence electrons does barium have? Sure. What is the symbol for barium? It's 2. Yes. What is the symbol for barium? It's Ba, right? Okay. How many valence electrons does polonium have?
6.
6. Okay. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6.
So you just basically go to the previous noble gas and then just count and skip D?
That's right.
Okay.
Questions? Okay. Okay, so this is just showing us everything that you guys learned, and now we get to talk about Lewis structures, right? So when we start talking about those valence electrons, we start representing them as dots, okay? So sodium has 1 dot because it has 1 valence electron. Magnesium has 2 dots because it has 2 valence electrons. Aluminum has 3 dots because it has 3 valence electrons. Silicon has 4 dots because it has 4 valence electrons. And then phosphorus has 5 dots because it has 5 valence electrons. Sulfur has 6 dots because it has 6 valence electrons. And chlorine has 7 valence electrons, so 7 dots. And then argon is a noble gas. It's stable. It has 8 dots. Now, the goal is to try to have it so that you have 8 dots around it. Right? And if you have 8 dots around you, then you want to be sure that you're stable, right? So 8 dots means that you're stable. Okay, that's our goal. So
I have a question. Does it matter where you place the dots? Does it have to be that way?
So if you have 8 dots, you want it 2 here, 2 here, 2 here, 2 here, because we know that they pair up, right? How many electrons are in an orbital? 2, right? So you want them to be paired up. So that's usually what they'll do. They'll pair up, right? So in the case of magnesium, we'll put both dots there because they're paired up. They're going to be in the S orbital, not the one.
Okay, and then it just goes clockwise around it?
It doesn't matter. You can go clockwise.
Okay.
As long as you started with them pairing up, right? So like here, these guys, since it's going to be the S paired up. Here, this guy's going to have 2 in the 2S. So we have 2 of them paired up and 1 free. Here we have 2 in the S, 2 in the P. Well, here's the S occupied, and then it puts 1 in each of the orbitals. Right. Here we have a total of 5 electrons. So you have 2 in the S, 1 in each of the P orbitals. And then we have 2 in the S. We have 1 in each of the P, and then we have an additional 1. So, okay, does that make sense?
Yes. So like in an odd number for the P's, you have to place 1 in each orbital. You can't leave them empty.
Yeah.
Okay.
Good question. Okay, so sometimes you'll get a question like this. It says, write the electron configuration for the highest occupied energy level group for 6A or 16. So we're looking at group 16. So let me give you a hint. You're going to write in, and then you need to tell me how many electrons are you going to have in the S, and then how many electrons would you have in the P. for anything that's in group 16. And S, tell me the number that's next to my S. 2. Okay. And then NP, if it's group 16, how many electrons have to be? 4. That's all they're asking. Okay. So
why is there an N?
N
represents
it represents any period that we have, right? So we know it won't be in the case of 1, right? But period 2, period 3, period 4, period 5. So as we go down, it represents any of the possibilities that could happen there. So that's how we use N, right? And so in that case, we can go up to 8 or 24. That would still work because there's the ability of us having more elements. So N represents the period. Okay. Let's get close to that time. That's what I just tell them. I need a couple more minutes. We're almost done. Feeling pressure. Okay. So identify the group whose electron configuration for the highest occupied energy level is N2, NP2. I'm sorry, NS2, NP2. So which group has 2 in the S orbital and 2 in the P orbital?
Is it 2A/14?
No, it would be not 2A.
Oh,
If it's 6A/16, so then it must be take 2 from it. Because your 14 is right. So it'll be 4A, that's right. 4A. Because remember, A just represents the A main group where you're starting with period 1 and period 2, and then you go to period 3, group 1, group 2, group 13, group 14, group 15, group 16, group 17, group 18. That represents your main groups. So it will be A/14, right? Because how many electrons, if we're in carbon, how many electrons do we have in the S orbital and in the P orbital for period 2?
Is it 2 and 2?
2 and 2. If I'm lead, how many do I have for the S orbital and the P orbital? Was it? It's 2 and 2. So anything that's in that group is always going to be 2 and 2. 2 in the S and 2 in the P. So that's all it's asking.
So like you have multiple answers for those?
Yeah, so the question is they want you to identify the group, right? So the group is group 14. You could say 4A if you guys know the main group, /14, right? /14 means group 14.
Can you show us on the periodic table? Because I don't know what you're talking about, 4A and 14.
I will show you the periodic table. Okay, so here we're on the periodic table, you guys see? Okay, so group, right? Up top are groups. So for group 14, that means here's the S, here's our P, right? So if I'm in group 14, that's this whole group. How many do I have in the S? I have 2. I'm always going to have 2 here, right? And then
yeah,
have in the P.
Oh, okay. Okay.
2, right?
2.
Okay, so don't overthink it, right? Because the question
that's what I was doing. Yeah, that's confusing.
It's that in that throws everybody off because they're saying if you're in any period, right? And you have 2 and 2, what group are you talking about? So for instance, if I ask you, if we have NS2 P NP5, what group am I talking about?
17.
Group 17, right? 1, 2, 3, 4, 5, 6, 7, right? That's 1, 2, 3, 4, 5, 6, 7. Just count the number of electrons across. That's all you got to do.
So why was the 4A put again?
It's because the old periodic table, because they're doing it for US and international. International just uses this periodic table that you guys see here. That's what everybody in the world uses. In the old days, we used to use the main group, which the main group was, this would be 1A. This would be 2A. This would be 3A. This would be 4A. This would be 5A. This would be 6A. This would be 7A. And this would be 8A. Right? We would ignore these, right? These would be the B group, right? They're second-class citizens, right? Transitional metals wanted their freedom, so we made them part of just a single group. Read the transitional metals. Exactly. Yep. Okay, so does that help? You know, when I was literally when I was taught chemistry initially, I had an instructor says, don't worry about this. You're never going to need it unless you go into materials, right? And then the next professor said, oh, you're going to need it, but there's a couple things that we're still trying to figure out. And then the third semester or third quarter, then they're like, okay, you need this, and this is what you need to know, right? So it took 3 quarters to sit there and get to the point where we need it. Questions? No questions? Concerns? Cash? Don't overthink it. Okay. So, I know we're working on that last part. Okay, so we've already talked about the Lewis structures, okay, or Lewis symbols. So that's just basically putting your valence electrons around the element. So tellurium has how many valence electrons? You told me? Tellurium, Te, has how many valence electrons?
Six.
6. So since it has 6, we're going to put 6 dots around it. 2 here, and 1, 1. Okay. So again, your goal is to get to your octet. Octet is stable. So that's just like the noble gases. Remember, the noble gases are the cool kids, right? I showed you guys that video, right? Did I not show you guys that video? No?
We have not watched the video.
Okay. This morning I showed you guys that video. Now, when I show it to you, I don't want to hear you showed us that. Okay. Let me.
I see the Did you see this?
Yes, you've seen it. Yes, you have. So,
Oh.
like I tell you, you guys have seen it. I know you guys have seen it.
Can't get it now. I can't get it now, but I can get it. Can't get it now. I can't get it now, but I can get it. Walked up the stairs. Walked up the stairs. Can't get it now. I can't get it now. I can't get it now. Cause the pocket's downstairs. I'm going to quit. The pocket's downstairs. I'm going to quit. I can't get it now. I can't get it. I can't get it now, but I can get it. Can't get it now. Can't get it now, but I can get it. Can't get it now, but I can get it. I walked up to beds. Walked up to.
Okay. See, I told you. You seen it, right?
I'm not gonna be able to sleep now.
Exactly what I was going for. Okay, so there's a couple things that you guys want to take into consideration. One of those things, what happened when we had potassium and water?
Explosive reaction.
Explosive reaction, right? So we know that group 1 metals, they're going to be very active. They want to get rid of that electron. And so they're going to pop off, right? I talked to you guys about that at the beginning, the very beginning of the semester. I also talked to you guys about carbon. I said that carbon's a Bohr, right? One of the reasons why carbon's a Bohr is because it's flexible, right? It can either give up 4 electrons or it can take 4 electrons. It can have 4 attachments, right? Okay, so it's a nice little video to remember things, right? You guys will never forget about carbon, will you? So. Back. Okay, so we've talked about trends already, right? So the atom is going to increase or decrease as we go from left to right.
Decrease.
Are you sure? You said, how would you say, increase or decrease?
Decrease.
Decrease, that is correct. Okay, so this is the trend. As we go from left to right, the atoms are going to decrease. Okay, so left to right, decrease, or from right to left, increase. And it also is going to increase from top to bottom. Okay, so if we have atomic numbers 15, 16, and 33. 15, 16, and 33. Give me the biggest from the smallest to the biggest. So who's atomic number 15? Is that phosphorus?
Phosphorus.
Okay. Who's number 16?
Sulfur.
And then 33? Arsenic?
Arsenic.
Okay. So who's going to be the biggest?
Phosphorus?
Are you sure?
Yes.
Yes.
You want to put money on that?
I'll go liquid or not.
Anybody want to put money on that?
Is it? I'm not sure if it's arsenic or sulfur because arsenic is lower and sulfur is more to the right. So I would say sulfur.
So anytime that we have to go lower, that means it's going to be bigger than the one above it. So in this case, arsenic is going to be our biggest, right? And then who's going to be the next biggest?
Sulfur.
Sulfur? No. Phosphorus.
Phosphorus, that's right. Phosphorus is going to be bigger than sulfur.
Because the left to right atoms get smaller.
That's right. Yeah. Okay, so that should be our correct answer. Good job, good job.
Oh, yeah.
Okay. Ionization energy. So ionization energy is the energy to ionize, to make an ion. So in other words, you're going to be removing one electron, right? So it's the energy to remove one electron. Now you're taking an electron. Think about it like this. If you're taking an electron, are you going to be willing? Okay. Are you going to be willing to give up that electron if you're so close to being a noble gas? So for instance, let's go to our periodic table. Okay, we're over here, right? Now you need to gain an electron, not lose an electron. Are you going to be willing to lose your electron?
No.
So that means you're going to fight more, right? So it's going to take more energy to remove that electron. So it's going to have a higher ionization energy. Now, over here, these guys want to do what? Group 1 metals? Do they want to gain electrons or do they want to lose electrons?
They want to lose them because they're closer to helium?
That's right. They're closer to being, lithium is closer to helium, right? It wants to get rid of that one electron. So is it going to be really hard to get that electron away from helium? That's going to be pretty easy. You're going to be like, oh, here, go ahead, take it, right? So it's going to have a lower ionization energy than, let's say, fluorine. If you're helium, right, a noble gas, are you going to want to give up your electron? You're stable already.
No.
Somebody's going to take you, make you poor. Are you going to be like, okay, yeah, go ahead, take it? No, you're going to fight, right? So it's going to have a very high ionization energy, right? Okay, so ionization energy is going to increase as we go from left to right. And then as we go from top to bottom, what do you think is going to happen?
It's
decrease, that's right. So it's going to decrease as we go from top to bottom. So we could say it's going to increase as we go from bottom to top. So these guys are going to have higher ionization energy than these guys have. Okay. Now, the second ionization energy is to say that you've already removed one electron. Now you're going to remove another, right? So group 2 metals, right? They need to remove 2 electrons. You've removed one of them already. Are they going to have a high ionization energy or are they going to have a low ionization, second ionization energy? Group 2 metals, you've removed one electron already, right? And so its second ionization energy, is that going to be high or low? For group 2 metals.
Low.
It's going to be low, that is correct. Why?
Because it has less, so it's willing to lose more.
It needs to lose one more. It wants to lose one more to be like a noble gas, right? Because it's in group 2. So here, we're right here, right? In the case of magnesium, you've lost one electron. It needs to lose 2 electrons. It's going to be excited. It's like, hell yeah, here, take it. It's yours, right? You don't have to fight me. It's all yours. It's free. You know, take it. Okay. So there's not going to be, it's going to have a very low ionization energy. Okay. So let's see those trends. This is just showing you that concept of ionization energy. You're losing an electron. So here's the trends. Helium, neon, all of these guys have high ionization energy, where as we go down the periodic table, they're going to have less. Okay. Talked about the third ionization energy, or second ionization energy, and then it's going to get more complicated with the third. It's the general trend. It increases from left to right and from bottom to top. Okay, so knowing that, we have beryllium, we have nitrogen and fluorine. Who's going to have the highest ionization energy and who's going to have the lowest ionization? So we're going to go from low to high. Give me the order.
Did you say low to high or high to low?
We're going from low to high. Who's gonna
So BE would have the lowest?
okay, BE. Then
Nitrogen?
nitrogen.
It's already in order.
Oh, it's already in order. Perfect. That's right. It's already in order. Yes. Fluorine is going to have the highest ionization. Okay, now we're going to talk about chemical families. You guys are already familiar with this because we kind of talked about this in the very first days. Alkali metals. Which group is alkali metals? Alkali. Are you sure? Alkali metals. Group 1. Alkaline metals. Group 2. We know that group 1 metal always wants to do what? They want to give away that electron. That is correct. That is correct. Alkaline metals want to give up how many electrons?
All of them.
Not all of them. Not none.
Some.
No, not some. Give me a number, damn it. 2. 2, right? Where's it located at? It wants to be like a noble gas, right? So it wants to get rid of 2. Okay, so we know that groups are going to behave very similarly, right? So group 1 metals, all of those guys are going to want to try to give up 1 electron to try to be like the noble gas. So they're going to be very volatile. They're going to be very reactive. This is just kind of showing you. You have lithium that gets all smoky and puffy. And then you have sodium, which gets all popped off and flashy. And then that's the same thing that happens with potassium, right? So when we get to halogens are one away from being a noble gas. They're also going to want to pop off, right? They're like, give me that damn electron. I will take it from you. I'm not going to give it, right? Give it nicely or I'm taking it, right? So because of that, they're going to be very reactive as well. And this is just basically showing us that, right? So if we had chlorine and phosphorus, very reactive reaction, right? Are you at 50 so far? Almost done. Okay, so these are the chemical families, right? And this is kind of the organization. Now you'll notice that the metals are over here. Alkalines are the metal of metals, right? So they're the most metalless metals, right? And then these are non-metals over here, right? So if we think about in terms of the ones that are most metallic, it's always going to be going from right to left. Like so in this direction. Which makes sense. You go from non-metals to metals, right? Okay. And then the ones at the bottom are going to be more metal-like than the ones at the top. Okay. Let's see. This is just basically showing us more chemical families. You guys have talked about the halogens. So metals, characteristics of metals, they're going to be lustrous, they're going to be malleable, they're going to be good at conducting heat and electricity, they're going to be ductile. Malleable basically means that we can kind of flex them around and beat them up a little bit, string them out for ductility. Lustive means shiny. You guys did that in the characteristics earlier, right? Shiny, all of that. Okay, non-metals are going to be brittle, dull, poor conductors of heat, or they're going to be gases, right? So metalloids are going to have characteristics of both metals and non-metals. This is just a summary of some of the physical and chemical properties of metals and non-metals. We know poor conductors of heat and electricity are going to be metals or non-metals. Got a 50-50 chance, metals or non-metals, or conductors of heat and electricity. Non-metals. Malleable, metals or non-metals. Brittle. Okay. So this is just showing us metals and non-metals and metalloids. You guys have a nice table, so you shouldn't get that mistake. So this is just showing us how metallic characteristics are increasing, right? As I said, from right to left and from top to bottom. Okay. Questions, concerns, or cash?
Yeah, I have one. Just to recap. So like on the periodic table, the size decreases from left to right, and then it increases from top to bottom. But in ionization energy, it increases from left to right, and it decreases from top to bottom.
Okay. Yes.
Okay, I was just making sure I got that right.
Okay. Any other questions? No other questions? Okay. Parnell, I guess I'll see you guys, or guys online, I guess I'll see you guys on either Thursday or Friday. And you guys have a good night.